Mabuhay, fellow physics teachers! Welcome to your program, Physics in Everyday Life. In a previous episode, we learned that light obeys the law of reflection, which states that the angle of incidence is equal to the angle of reflection. The images formed by mirrors can be found by tracing the path of the reflected light. Today, we will continue studying light and how images are formed. But this time, we will focus on lenses and their applications. So join us in an activity-filled episode about lenses at work here on Physics in Everyday Life. Can images be formed even without mirrors or similar objects? Let's find out from this demonstration. Our setup here consists of pinhole cameras and a bulb here. The camera consists of a box which is open at both ends. One end is covered with tracing paper that serves as the screen of the camera, and the other end is covered with black paper which has a pinhole in it. Let's now see how an image is produced. Alright, watch or observe the image formed by the pinhole camera. Now, suppose we make the hole larger, as in this case here. What kind of image shall we get on the screen? How do you compare this new image with the previous image? Okay, now, suppose we make several pinholes, as in the case here. What do you expect to see? Was your prediction correct? How many images are formed? Alright, how do we explain our observations here? Light rays from the different parts of the bulb's filament pass through the tiny hole of the camera. Since light travels in a straight line, light rays from the upper part of the object falls on the lower part of the screen, while the rays from the lower part of the object falls on the upper part. Thus, an inverted image is formed on the screen. Alright, if the hole is big, such as this case here, more light enters the hole and produces a bright, although not sharp, image. With a smaller hole, such as this one here, the image is dimmer but sharp and distinct. Now, with multiple holes, such as this camera here, we get multiple images. What happens when we place a convex lens between the pinholes and the light source? Okay, watch this. Describe the image on the screen. How do we explain our observations? Before we answer this question, let us find out what a lens does to light. First, let us examine how light behaves when it passes through a transparent material. Watch this. This bending of light when it passes from one material to another is called refraction. In this case, light passes from air to the glass and then back to air. Refraction is due to the difference of the speed of light when it travels in different materials. Light travels faster in air than in other materials. If you recall, refraction is a wave property. Do you know why this pencil immersed in water looks bent? This is because of the refraction of light. Because light coming from the pencil refracts or bends when it crosses the boundary between water and air. The refracted beam, which enters our eyes, gives the illusion of a bent pencil. Now, let us shine parallel light rays on a lens. All right? Observe now. Let's do the same thing with another kind of lens. All right? Perhaps you observed that the incident parallel rays were refracted in both lenses. In the first lens, the refracted rays converge at a common point, this point here, while in the second lens, the refracted rays spread out or diverge. The first lens, this one here, is called a converging or a convex lens. This lens is thicker at the middle than at its edges. The point where the rays meet or converge is called the focus, right here, and the distance from this point to the center of the lens is called the focal length. The second lens is called a diverging lens. If you examine this lens, it is thinner at the middle than at its edges. Although the refracted rays in this lens do not meet at a common point, if these rays are extended, however, they will appear to meet at a common point. This common point is called a virtual focus because the rays do not actually meet at this point. Now, how do we determine the focal length of a lens? A common method is to project the image of a distant object from this convex lens here on this particular screen. Rays from a distant scenery or an object are approximately parallel, thus the image of the object will fall on the focus of the lens. You will have to adjust the position of the screen so that a clear image is formed on it. Now, the distance between the lens and the screen is the focal length of the lens. We shall study how lenses form images when we return. Earlier, we saw how a lens can change the path of light by refraction. Now, let us find out how lenses form images. Our setup consists of an optical bench here, a lighted candle, a screen, and a lens. You will notice that some points on this bench are marked. The 1F here means that the distance from this point to the lens is equal to 1 focal length. The next point, 2F, is twice the focal length. Now observe the image on the screen as we change the position of the candle. All right? Okay, so we observe that When the object is at a distance greater than the focal length, such as this position, the image on the screen is inverted and smaller than the object and nearer to the lens than the object. Okay? The image is real because the refracted rays actually fall on the screen to form the image. As the object is moved nearer the focus, the image is still real, inverted, and becomes bigger than the object. The position of the image is farther than the position of the object from the lens. Now, let us position the candle at the focus, right here. All right, so is there an image formed on the screen? Well, yes, there still is, but note that the image distance is very much greater than the focal length. Theoretically, the image is at infinity, so we can interpret infinity to be relative to the focal length of the lens. Finally, let's position the candle between the focus and the lens, okay? No image is formed on the screen, but if we look through the lens this way, all right, I'll remove the screen. If we look through the lens this way, we can see the image on the same side of the lens as the object. The image is upright, bigger than the object, and virtual. Okay, what about a diverging lens? Does it form images like a converging lens? All right, we'll have here the diverging lens. Take this out. All right, let's start again from the farthest end here and put the screen on this side. Let us find out. Okay, so let's move this object nearer the concave lens. Okay, do we observe any image on the screen? We did not observe any image projected on the screen. This is because diverging lens is only capable of forming virtual images. These images cannot be projected on the screen, but again, if we look through the lens from this side, you can see it on your screen now, we can see the image of the object. All images formed by a diverging lens are upright, diminished, and located on the same side of the lens as the object. For a converging lens, the image formed can be real or virtual, inverted or upright, diminished or magnified, depending on the location of the object. Now, let us explain the function of a lens in multiple pinhole cameras. Without a lens, a multiple pinhole camera produces multiple images. But with a lens slid in front of the pinhole, the multiple images converge into one bright image. The lens collected all the beams from the different holes, refracted them, resulting in one bright image on the screen. We will study the camera in more detail when we return. Stay tuned. Do you know that the human eye and the camera resemble each other in many ways? A lens camera basically consists of a light tight box here, an aperture right here, a shutter, and a photographic film, plus a converging lens system right here. A viewfinder is used to aim the camera and to see what will be included in the photograph. To make a correct exposed photograph, the aperture controls the amount of light that enters the camera. It corresponds to the hole of a pinhole camera. The aperture can be made smaller or bigger to produce correctly exposed photographs. An overexposed photograph is due to too much light. To avoid unnecessary exposure, the shutter opens only when necessary. The film corresponds to the screen where the image is projected. The lens system of a camera consists of not just one lens, but several lenses to eliminate the lens aberrations, such as a blurred image or an image with colored edges. But this lens system behaves like a simple converging lens. All right, let's now look at our diagram here. You will notice that from our diagram here, each part of the camera has a corresponding part in the eye. For example, the cornea and the lens correspond to the converging lens system of the camera. The eyelid corresponds to the shutter, and the pupil, right here, which controls the light that enters our eye, corresponds to the aperture of the camera. The retina, here, acts as the film of a camera. Since they have the same parts, they produce image in a similar manner. We will use the camera to understand how an image is formed. A single lens camera works like this. Light rays from the object enter through the convex lens. The convex lens will refract the light rays and form an inverted image on the film of the camera. Earlier you learned that for a convex lens, a distant object forms an image farther from the lens. Thus, in the camera, the lens position is adjusted depending on the position of the object. For instance here, when the object is far from the camera, then the lens is moved nearer the film. While when the object is nearer the camera, then the lens is moved farther from the film. But what is the difference between our eye and the camera? A camera adjusts the distance of its lens to accommodate different object distances, while it uses a fixed focal length lens. Now, the eye does the reverse of the camera. Its lens position is fixed, but the focal length of the eye lens is adjusted. How does the eye adjust its focal length? It does this through the ciliary muscles that surround the lens of the eye. Imagine this to be the lens, and the ciliary muscles are around this. So, for example, when the eye looks at a distant object, the ciliary muscle relaxes and the lens becomes less curved. When less curved, the focal length increases and an image is formed on the retina. The eye, like a camera, forms an upside-down or inverted image. But why don't we see everything upside down? Because our eye never learns that way. It has no secret eye which looks into our eye and see an upside-down image on the retina. What our brain gets is a set of messages from our retina. Since we were born, we learn to accept the messages from the upside-down image as a picture of an upright image. Let's look at our model eye here. You can see that it is made of a curved jar. This corresponds to the lens of the eye, and this corresponds to the retina. Watch what happens as light shines on it. All right. So for a normal eye, this is what happens. You can see that the light is focused exactly on the retina here. Now what happens when the eye loses its ability to change the shape of its lens due to old age or defective eyeballs? All right, let's move this farther away. When the image of a far object falls in front of the retina, such as this case here, This is a case of nearsighted vision defect. This can be corrected by using a diverging lens. So watch this. All right? Now, when the image of a near object, such as this one, falls behind the camera somewhere here, it is a far-sighted vision defect. This can be corrected by using a converging lens such as this. Okay? So, we will have more of lenses at work when we return. I'm sure you are familiar with these instruments. All of these instruments use lenses. This magnifying glass, which is made of a convex lens with a short focal length, gives us an enlarged, upright image when it is placed very close to the object. To enable the eyes to see the details of objects or organisms that are invisible to the naked eye, just like the sample here, a microscope is used. All right? This microscope consists of two convex lenses. The first lens is called the objective lens. These are the objective lenses. Remember our earlier demonstration? We showed that when the object is placed within the focal length of the converging lens, then the image formed is enlarged, upright, and virtual. That is why we see an image only when we see it through the lens. This is located near the object to be examined. The second lens is called the eyepiece lens, located here, near the observer's eye. Both these lenses have short focal lengths, but the objective lens has a shorter focal length than the eyepiece lens. Light coming from the object first enters the objective lens. The image is formed by this lens, and the image is real, inverted, and magnified. This first image will act as the object of the second lens. The second lens will now form a virtual, upright, and magnified image. In a microscope, the image will appear at a distance of about 25 centimeters from the eye, which is the normal nearest distance that we can clearly focus. A telescope, like this one here, has two converging lenses, just like a microscope. We have a setup here, which is a telescope. Its objective lens, which is situated somewhere here, has a very large focal length and is used to capture the light rays from a very distant object. These distant objects can be the moon or the stars. The image formed by this lens is real, inverted, and diminished. This image will then be magnified by the eyepiece here, which has a lens inside, and this lens has a short focal length. But the image is virtual, thus we can see it only by looking through the eyepiece lens. Many astronomical telescopes, just like what we have at the University of the Philippines Institute for Science and Mathematics Education Development, use concave mirrors instead of the objective lens. This is because lenses with very large focal lengths are more difficult and expensive to make than concave mirrors. Let us now make a brief summary of the important concepts and principles that we learned in today's episode. A pinhole camera forms a real and an inverted image. Light bends when it passes from one material to another. Refracted rays from a convex lens meet at a focus. Refracted rays from a concave lens spread out, and their extended rays meet at a virtual focus. Converging lens can form a real or virtual, an inverted or upright, an enlarged or diminished image, depending on the position of the object relative to the focal length of the lens. Diverging lenses can form only virtual images. The camera and the eye have the same essential parts. They differ only in their ability to accommodate different object distances. Accommodation is the ability of the eye to adjust its lens focal length. We hope that you enjoyed sharing this enlightening episode with us. Join us again next time as we continue to explore other properties of light. Till then, for Physics in Everyday Life, this is your host, Zenny Domingo. Hanggang sa muli. Bye!